Alright, so the first thing we need to do is take into account the forces acting on the bike. So for this example, I'm just going to use a brick lying on a table. This brick has, at the moment, two forces acting upon it. There's force gravity, and there's the normal force of the table that's pushing up against gravity. If we attach a rope to the side of the brick and start applying a force on that rope, a force tension, then another force is going to appear called force friction to resist the force tension. Now, any object that has a normal force also has what's called a force of static friction. And so if you come to this brick and start pulling on the string, any force you apply to that brick will not move it unless that force is greater than the force of static friction. To help understand this, you can imagine a car in a driveway. A car in a driveway is a very heavy object, so it has a large force normal, and that means it also has a very large force friction. So if you go up to your car and try and push it directly sideways, you're not going to get very far on your own because the force that you can apply to that car is nowhere near large enough to exceed the force of static friction and move it. What this means is, in this situation, unless the force tension is greater than the maximum force of static friction, these two forces are always going to be equal and therefore cancel each other out, because there's going to be no movement in the brick unless you can apply enough force to overcome the maximum force of static friction. Alright, so now that we've established that in a system with a force tension and a force friction, where the maximum force of static friction has not been exceeded, the force tension and the force friction will always be equal, unless of course that force tension rises above the force of static friction. In the next example, we're going to look at a spool of wire. So I have a small drawing of the wire up here so you can kind of get what this cross section is going to be. But this cross section is a side view of this spool. And so you can see here that the radius of the outer circle is 10 centimeters and the radius of the inner circle is 5 centimeters. So if we were to take a wire that was attached to this spool, let's say it comes off at this point here, and we're going to say apply a force tension to that wire. Now, obviously there's going to be a force friction resisting the whole thing to just start sliding backward, and that's going to be in this direction here. So now we have two forces, the force tension and the force friction. And because you can obviously see that this is either going to roll forward or roll backward. But it's obviously not going to just slide forward or slide backward, it's going to roll. And so because it's not sliding, we know that the coefficient of static friction has not been exceeded, and therefore these two forces will be equal. So you can see in this example here that what happens is it actually rolls backward. And there's a reason for this, and it has to do with torque. So torque is a force applied to a rotational axis. And so torque is equal to force times distance. But the trick is that the force and the distance have to be perpendicular to each other. So in this case, if we take moments about point A, which is the center of the circle, and that's also going to be the center of rotation, this force applied on the string is applying a negative torque to the system because you can see that it's going to want to rotate it clockwise, and that's negative. So this torque is going to be equal to the force times the perpendicular distance, which is 5 centimeters. So that's going to be, let's say that the force is going to be 10 newtons. So that's going to be negative 10 times 5, the distance. Force times distance, but again, they must be perpendicular. Now, again, this force friction is going to be equal to the force tension. But, as you can see, it's further away. So this force friction, as you can see, this one is trying to rotate it this way. The force friction is trying to rotate it in the other direction, counterclockwise. So it's going to be a positive torque. And because the force tension and the force friction is the same, it's going to also be 10 newtons. However, the distance here is different. The distance is 10. And that is what makes the difference. So again, the forces are the same. They're both 10 newtons, but the distances are different. So obviously, if we do the math, it's going to be negative 50 plus 100. So if we do the math, it's just going to be a simple positive 50. So if it's positive, it means that the whole system is going to rotate counterclockwise and it will roll backward, as you see in this example here. Okay, so what we learned from this example is that in this scenario, where a force is being applied to a string on a spool of wire, the equation that we can do to find out which way this spool is going to turn is this one here. And so remember, the two forces are always going to be equal, so the variable for them is going to be F. So the negative torque being applied to try and turn it clockwise is force times B, which is this distance here from there to there. The force trying to turn it counterclockwise, give it a positive torque, is the same force times the distance A from here to here. So from this example, I hope it's clear that as long as B is less than A, it will always result in a net positive torque and therefore roll the system counterclockwise backward. Okay, so now let's apply what we've learned to the bicycle. As you can see here, we have the wheel with force friction and the pedal with the force tension. Now, in this example, it's important to note that I am assuming that one rotation of the pedal means one rotation of the wheel, in which case it's got a 1-to-1 gear ratio. You move your feet around once, the wheel turns around once. If that is the case, then the equation for the total torque of the system is very similar to the circle. We have the forces are both equal, and so the negative torque on the pedal is equal to the force times the distance to the center of rotation, which is B here, negative FB. It's a negative torque. And the positive torque, which is the friction of the wheel resisting the turning, is going to be plus the force times the distance of the force to the center of rotation, which I've said here is A. Now, as you can see, in any case, the pedal of the bike, the length of the pedal of the bike is almost always going to be less than the radius of the wheel, just because of the engineering of the way bikes are made. So B will always be less than A. In that case, we see the same situation with the wheel. If we assume that B is 5 and A is 10, and let's say the force is 1 Newton, this is going to equal just 1 times 5, negative 5, and 1 times positive 10 plus 10, resulting in a net torque of plus 5. That's going to rotate the system backwards, as we saw in the spool demonstration. So, that's it, right? The bike would roll backward, end of story. Well, not exactly. There is still more to consider in this situation. If you remember me saying, I assumed that one rotation of the pedals equals one rotation of the wheel. But that is not always the case. As any of you who have ridden a bike or driven a car would know, bikes and cars have different gears, and that affects the gear ratio and therefore the torque. In a low gear ratio, if you rotate the pedals once, it might only rotate the wheel slightly, and this allows you to accelerate faster and get going, and also go up hills on a bike. Once you get up to speed or are going downhill, if you want to accelerate more, you go into a high gear ratio. And that would mean that with one rotation of the pedals, you would get more rotation out of the wheel, and therefore be able to maintain speed with less difficulty. So, Now, taking gears into account, theoretically there will be a gear ratio that will allow the bike to move forwards instead of backwards. Now, again, in all the previous examples I've shown, the gears have been the same size. Now, if we consider the size of the gear on the back wheel to be C and the size of the front gear to be D, that means that in all the previous examples, C over D, the radius of C over the radius of D has been equal to 1. They have been the same. And if you'll remember, if we assume that A is twice the length of B, and A will always be greater than B, in this example I'm just using double the length, that is equal to 2. A over B is equal to 2. Now, because A over B is greater than C over D, the bike will move backwards with a 1-to-1 gear ratio. But if the gear on the back wheel is twice the size as the front wheel, that means C over D is now equal to 2. And then C over D is equal to A over B. That means that there's no movement. Now obviously this would be very hard to recreate in the real world. It's very hard to get exactly the same gear ratios, and there's always going to be small alterations resulting in small movements. But theoretically, if they were exactly the same size, there would be no movement. Now, if C over D, if the size of C is greater than twice the size of D, that would mean that C over D is greater than 2, therefore greater than A over B, and the bike would move forwards. And so this equation, A over B equals C over D, theoretically you could use it for any bike, as long as you have the radius of the wheel, the length of the pedal, and the radiuses of the two different gear ratios. You can then decide whether the bike will move forward and backward using this equation. Now, here's my final answer to the riddle. There is really not a perfect way for me to guess the answer unless I measured the gears, measured the wheels, measured the length of the pedals, and then did the math. So for now, I'm just going to say that my answer would be whatever the result of this equation would be had I the opportunity to measure the gears and wheels of the bike that Veritasium is using in his video. That is my answer. I hope you've enjoyed. If you want to comment, if you disagree with what I've done here, please do so. I would love your opinions. Thanks for watching.